Artificial Intelligence for Industrial Engineering From Hype to Practical Productivity. Good afternoon, everyone. Respected members of the Indian Institution of Industrial Engineering, honorary guests, professionals, and friends. Thank you very much for inviting me. Today, we are going to talk about artificial intelligence, but I want to approach it slightly differently. I am not going to talk about AI merely as an IT technology, and I am certainly not going to present it as some magic solution. I want to look at AI in the language we engineers understand: machines, processes, productivity, quality, cost, reliability, safety, and decisions. And the one thought I would like us to carry throughout the session is this: AI should not replace engineering judgment, it should amplify it. Why are we discussing this now? Because AI is moving very rapidly from laboratories and software companies into actual industrial workflows. And therefore, for an engineer, the interesting question is no longer, can AI write something impressive? The more useful questions are, can it detect a quality problem earlier? Can it reduce a maintenance interruption? Can it help an MSME understand standards faster? Can it help us analyze production information? Can it improve planning? Can it help an engineer make a better decision? Interestingly, IIIE itself has brought artificial intelligence and industrial engineering together in its 2026 national theme around Viksit Bharat 2047. So this is not an isolated technology discussion. It is increasingly an industrial engineering discussion. My framing today will therefore be very simple: practical AI, engineering-led AI, and human accountable AI. Before going further, let us demystify AI. In very simple terms, an AI system receives some input, identifies or infers patterns, and produces some useful output. That output may be a prediction. For example, is this bearing likely to fail? It may be a recommendation. Which production schedule looks better? It may generate content, a draft SOP, summary, report, code, or checklist. Or in some systems, it may help trigger a decision or action. Now, let us translate that into engineering language. For a mechanical engineer, AI may look at vibration or temperature behavior and identify an abnormal pattern. For an electrical engineer, it could examine load or signal behavior and detect an anomaly. For an industrial engineer, it could analyze production, capacity, inventory, quality, or workflow information. So AI is not necessarily a robot. AI is not necessarily ChatGPT. AI is essentially a new capability for recognizing patterns, making predictions, generating information, and assisting decisions. But there is a condition: it becomes useful only when it connects to a real workflow: planning, monitoring, diagnosing, optimizing, documenting, or deciding. Otherwise, it remains an interesting demonstration. We also use the word AI very loosely today. So let us separate a few things. At the first level, we have automation. If temperature crosses a particular threshold, activate an alarm. If a part fails inspection, move it to rejection. That is predefined rule based logic, and industry has used this for decades. Then comes machine learning. Instead of giving every rule ourselves, we allow a system to learn patterns from historical data. Then deep learning becomes useful for more complex information: images, signals, audio, and language. Then we have generative AI, which many of us have experienced recently. It can create text, code, summaries, analysis, and structured information. And now we are entering the age of AI agents, where systems may follow multi step workflows and use different tools. But here I would suggest a very important engineering principle: do not use AI merely because AI is available. If a checklist solves the problem, use the checklist. If Excel solves it, use Excel. If a sensor threshold solves it, use the threshold. We should move to more complex AI only when the problem actually requires it. In engineering language, fit the technology to the problem, not the problem to the technology. Let us now make this even more familiar. For our mechanical engineering colleagues, the world consists of machines, motion, heat, materials, vibration, wear, tolerances, loads, and failures. AI gives us another way of recognizing patterns in this behavior. For our electrical engineers, we have signals, sensors, circuits, motors, drives, controls, and power quality. Here again, AI can help convert enormous streams of signals into detection and prediction. Now come to industrial engineering. We are looking at people, processes, time, cost, quality, inventory, layout, flow, and productivity. So, industrial engineering is actually very naturally positioned to use AI because IE already works across the whole system: machines, methods, materials, people, information, and management decisions. I therefore like to describe AI to engineers as a sensing, reasoning, and decision support layer added on top of our existing engineering systems. It does not remove the engineering underneath. Another way engineers can understand AI is through a familiar control system type view. We have inputs. These inputs may be sensor readings, images, drawings, ERP data, SOPs, inspection reports, or maintenance records. Then comes the AI model. It processes these inputs and infers patterns. Then we receive an output: prediction, classification, summary, recommendation, or perhaps a plan. But notice what comes next: engineer check. Does this match the standard? Does it match the calculation? Does it match what is happening on the shop floor? Does it match physical reality? Then comes feedback. Errors are corrected, data improves, the system improves. This is why I would hesitate to say that AI knows something in the same way an experienced engineer knows a machine or a process. AI infers from information, and therefore verification remains part of the system. Now we come to the practical part. Where can industrial engineering actually use AI? Almost everywhere, but in very different forms. Take time and motion. Video and production data can help identify cycle time variation and possible ergonomic concerns. Take layout and flow. We can detect bottlenecks, simulate scenarios, and increasingly test alternatives through digital twins. In planning and scheduling, AI can assist demand forecasts, capacity planning, and rescheduling. In quality, computer vision can assist inspection, while analytics can identify abnormal SPC patterns and help generate RCA hypotheses. For maintenance, vibration and temperature behavior can support early warning systems. In the supply chain, AI can analyze supplier risk, inventory behavior, and disruption signals. And one area that is particularly interesting to me is standards and compliance. Imagine an organization with hundreds of standards, SOPs, customer specifications, and regulatory documents. Instead of an engineer spending hours locating information, a controlled knowledge system can help retrieve the relevant sections much faster. But please notice my choice of words throughout: assist, support, identify, not blindly decide. That distinction will become important later. What changes when these capabilities become embedded into industry? The transition is quite interesting. We move from fixed automation towards more adaptive assistance, from monthly or weekly reporting towards real time signals, from waiting for equipment to fail towards predictive health monitoring, from doing every physical trial first towards greater use of simulation and digital twins, from searching folders and manuals towards knowledge assistants, and from optimizing isolated departments towards increasingly looking at the complete supply chain. So the real change is not simply that factories are getting another software package. The bigger change is that the time between data to understanding to decision is becoming shorter. And that can be extremely powerful, but only if our data, processes, and controls are good enough. We are already seeing this in industry. Siemens has demonstrated generative AI assistance around industrial automation and engineering workflows. BMW and Nvidia have demonstrated digital twin approaches for virtual factory and production planning. Computer vision systems are increasingly being used for visual inspection, and predictive maintenance systems analyze vibration and temperature behavior for equipment health signals. Rather than me describing all four, let us quickly see one. Before starting video, while watching, don't focus only on the futuristic interface. Watch one thing. What part of the engineer's workflow is becoming faster? Now we play this clip. That is the useful question with any industrial AI demonstration. Not how impressive does it look, but which engineering task became faster, safer, more consistent, or more informed. Now somebody may reasonably ask, do we need to build an AI laboratory to start? Usually no. There is already a first layer of readily available tools. General enterprise AI assistants can support reports, SOP drafts, training material, meeting notes, and document analysis. ERP and business systems are also bringing AI assistance into planning, inventory, service, and reporting workflows. Then there are internal knowledge systems. Imagine being able to ask your organization, show me every previous complaint associated with this component, or find the inspection criteria from our relevant SOP, or compare these two supplier requirements. Office and analytics tools are also increasingly incorporating AI. For many organizations, this is actually the sensible starting point because the investment and integration are relatively manageable. The selection rule I would suggest is high human effort plus verifiable output plus manageable data sensitivity. That is a good first AI use case. Then we have a second layer, much closer to the shop floor. Here, the implementation becomes more engineering intensive. Industrial co-pilots can support automation engineering and troubleshooting. Computer vision can assist defect identification, safety checks, counting, and traceability. Predictive maintenance systems combine equipment data with machine learning models. Digital twins can support layout evaluation, robotic simulation, and virtual commissioning. These can create much larger value, but they also create larger responsibilities. Now, sensor location matters, data quality matters, machine integration matters, cybersecurity matters, system maintenance matters, and somebody must own the model and its output. So, the closer AI gets to the physical process, the stronger our engineering governance needs to become. I will take just 1 minute here to connect this with some of the work we have been exploring at VoidPrakash Research Consultancy. Our approach has been less about creating AI for the sake of AI and more about using it as a research and technical intelligence accelerator. For example, in regulatory and standards intelligence, AI can help us search, classify, and compare large amounts of technical information. In industrial research, it can assist literature, patent, competitor, technology, and market scanning. For MSMEs, structured research can be converted into checklists, SOP inputs, export readiness documents, and decision notes. And industrial observations or documentation can be converted into more usable workflows and management information. But our working principle remains the same. AI accelerates search and synthesis. Human technical judgment verifies relevance, risk, and final action. That, I believe, is a healthier industrial model. And this brings us back to industrial engineering. The technology may change, the fundamental questions don't. How do we improve productivity? How do we reduce variation? How do we improve flow? How do we design safer and better work? How do we improve value while controlling cost? These are industrial engineering questions. AI simply gives us faster ways of measuring, detecting, analyzing, and sometimes predicting. So I would write the relationship as industrial engineering plus data plus AI, leading potentially to faster insight plus better decisions plus accountable improvement. IE remains the operating system. If we map it across an organization, the opportunity becomes very broad: planning, quality, maintenance, supply chain, inventory, energy, compliance, R&D, management. But don't try to implement everything. Every organization should ask, where are we repeatedly spending engineering time on analyzing information? Where are decisions slow because information is fragmented? Where do patterns exist that humans cannot easily see at scale? That is where I would look first. Let us take one practical workflow that brings several of these ideas together. Imagine a small or medium manufacturer in Madhya Pradesh who wants to sell a product into a new overseas market. The manufacturing team may know perfectly well how to make the product. But now another chain of questions begins. What exactly is the product classification? Which market are we entering? Which regulations apply? Which standards apply? What testing is required? What documentation is required? What could prevent market entry? Traditionally, this could require considerable manual research across many documents. AI can accelerate parts of this process. It can help search documents, compare requirements, build preliminary matrices, generate checklists, identify possible gaps, summarize information. But here's the crucial point. Suppose AI identifies the wrong revision of a standard or misunderstands whether a regulation applies to that particular product. A beautifully written answer can still be wrong. Therefore, the final workflow must be product to market to rules to standards to risks to action plan. AI can accelerate the middle, but an engineer or competent professional must verify the evidence. This distinction between speed and accountability is one of the most important things we need to preserve. Let's take a second example, which is even more familiar. Suppose rejection suddenly increases. An AI system can look across historical information and ask, did it happen predominantly on one shift, one machine, one supplier, one material batch, after one maintenance intervention, or under one particular process condition? That is extremely useful because the system can identify relationships across much more data than a person might inspect manually. It might then say, these are the three most likely relationships worth investigating. Excellent. But has AI completed the root cause analysis? No. It has generated hypothesis. Now we go to Gemba. We examine the machine. We inspect the material. We review the process. We perform tests. We check the drawing or specification. And only when evidence supports the cause do we implement and validate corrective action. So I would phrase the division of labor like this. AI is very good at asking, where should I look? The engineer must still answer what actually happened and what corrective action is technically justified. This leads to perhaps the most important statement in today's talk. AI should be a co-engineer, not an oracle. The engineer frames the problem. AI can identify patterns and create alternatives. Evidence comes from the machine: measurements, standards, drawings, calculations, and site reality. Then the engineer makes or approves the verified decision. My simple rule is human in the loop. As systems become more capable, human on the loop, but never human out of accountability. especially where safety, compliance, reliability, or significant financial consequences are involved. We cannot say the AI decided. Engineering accountability cannot disappear simply because the software became intelligent. Now, there is another reality, particularly for MSMEs. Sometimes people say AI sounds very good, but our factory doesn't even have perfect digital data. That does not mean you cannot begin. Think of four levels. At level 1, much information may still be on paper or inside people's experience. AI may help structure SOPs, checklists, and templates. At level 2, there are Excel sheets and organized folders. Now, summaries, comparisons, and basic analytics become possible. At level 3, you have ERP, CRM, quality and production data. Now, dashboards and anomaly detection become more practical. At level 4, machines and sensors become connected. Now, predictive applications become much more powerful. The message is start where your data actually is. Don't purchase an expensive AI system merely because somebody says Industry 4.0. Improve the information system step by step. Up to this point, I have discussed opportunities. But engineers are trained to think about failure modes. So, what are the failure modes of AI? The first is hallucination. AI can produce something that sounds completely confident and still be incorrect. That makes engineering verification essential. Second is confidentiality. Imagine somebody uploading proprietary drawings, customer data, supplier pricing, or manufacturing know how into an unsuitable public AI system. That could create an entirely new information security problem. Third is automation bias. We tend to believe polished outputs, but confidence of presentation is not evidence of correctness. Fourth is data drift. Machines change, suppliers change, processes change. Products change, people change. A model that performed well yesterday may not continue behaving identically. And then we have cybersecurity. Every new connected intelligence system may create another attack surface. So, trustworthy industrial AI requires validity, reliability, safety, security, accountability, transparency, and privacy. In many ways, this is familiar territory. We already manage risks in engineering. AI governance should be viewed as an extension of that same professional discipline. So, if tomorrow an MSME owner asks, where do I start? I would not recommend beginning with a massive digital transformation budget. Start with three painful problems. During the first couple of weeks, identify activities that consume time and have measurable outcomes. Then map the data. Where does the information come from? Who owns it? Is it confidential? How will AI output be verified? Then create a small pilot. Perhaps an SOP assistant. Perhaps quality report analysis. Perhaps supplier comparison. Perhaps maintenance log analysis. Perhaps a compliance research workflow. And then measure it. Did we save time? Did accuracy improve? Were errors reduced? Did people actually use it? Were there new risks? Only then scale. So, my practical recommendation is start small, verify deeply, scale responsibly. What does this mean for engineers ourselves? Do all industrial engineers now need to become computer scientists? I don't think so. But we do need several new fluencies. First, problem framing. AI gives much better results when we define the engineering problem clearly. Second, data literacy. We need to understand what our data proves and what it does not. Third, workflow design. Rather than asking AI random questions, engineers should learn to integrate it into structured tasks. Fourth, verification discipline. Sources, calculations, assumptions, exceptions. And fifth, change management. Because factories are socio-technical systems, introducing AI means changing people's work, not merely installing software. So my future-ready formula would be engineering judgment plus data discipline plus AI fluency. I will close with one thought. Much of the public discussion around AI is framed as engineer versus AI. I don't think that is the most useful comparison. The more realistic comparison may increasingly become engineer using AI versus engineer not using AI. Artificial intelligence will not remove the principles of industrial engineering. We will still pursue productivity, quality, reliability, safety, optimization, cost effectiveness, and continuous improvement. What AI changes is the amount of intelligence and analytical capability available to us while doing that work. If engineers lead its implementation with discipline, evidence, and accountability, AI can become an extremely powerful extension of industrial engineering. Thank you very much. And I would be very happy to take your questions.